Lesson 10 Building Logarithmic Table starts with the opening exercise where they give us in the left-hand column the what power 10 with the 1,000, and then they give us the log base 10 of 1,000. So remember, by this point, we know that the what power version means the exact same thing as the right-hand side version. So rather than doing both columns, what we're going to do is we're going to reference both in that design. So whether you go with the what power 10, so if you say 10 to what power is 1,000, or if you say log base 10 of 1,000, either way your answer for this one is going to be 3. And that's because 10 to the third power is 1,000. So we'll do the same thing here. 10 to the second power would be 100, so the answer is 2. 10 to the first power would be 10, so this ends up being 1. 10 to the 0 power would be 1, so this ends up being 0. And then 10 to the 1/10th power, this would be -1, and 10 to the 1/100th power is going to be -2. So they ask us in this one to formulate a rule based on your results above. If k is an integer, then log base 10 of 10 to the k power is equal to what? And we would have to say that is equal to k. So that would be the result there. So in this section, we're going to do is we're going to explore building logarithmic properties that we're going to see develop over the next several sections. So by starting with number 1, it says to find two consecutive integers with the powers of 10, so that way 30 is between them. Or in other words, they're asking us to figure out 10 to what power would be just under 30, and 10 to what power plus 1 would be equal to something above 30. So it turns out when we solve this one, if we tried 10 to the first power, we would get 1. If we tried 10 to the second power, well, this would not be 1, it would be 10. If we tried 10 to the second power, that would be 100. So 10 is below 30 and 100 is above 30. So our statement would say 10 to the first power is less than 30, which is less than 10 to the second power. So that would be our result in that one, which actually carries us into here. What were the two integers? The integers were 1 and 2. And so 3 says find a number k so that the one decimal place is that. I think I have another space over here for that. I made some more room. So it says find a number k to one decimal place so that k, 10 to the first power, the same piece over here, and use that to find an over and under estimate for that value getting one place to the decimal. So basically what they're asking us to do is we may want to consider drawing like a little table of values to help us organize. What we're going to do is we're going to choose some x values right here, and we're just going to raise them 10 to the x power. And so perhaps, right, remember we said we started off with 10 to the first power, so maybe we'll try 1.1, 1.2, 1.3, 1.4, and maybe 1.5. And our goal is to see how close we can get to 30 without actually going over 30. So when we do that, right, that's what we're going to look at. And so when we plug that in, and again, we're doing with a calculator, so you may want to have a calculator handy in this design. So that way you could type in 10 to the 1.1 power. And so when you do that, you're going to get 12.5 or 12.6. If we did 1.2, we're going to get 15.8. If we did 1.3, we would get 19.9. If we did 1.4, we would get 25.1. And if we put the next one in, we would get 31.6. So what we can see is that if we are raising this to these powers, let's change colors of that, 1.4 is as close as I can get without going over 30. So I know that my lower bound is going to be 10 to the 1.4 power. That would be less than 30. Less than 30. And what they want us to do again is they want us to find out what would be on the other side of that over here. So once we find that, we can do our K value. We can add 0.1 to it. So we find out we end up at 10 and then 1.5. And again, you can see that by our table, we are just over in the next one. So I'll just make this table bigger. That shows that these were the two values that we used to represent that. So they're going to ask us in number 4, what if we took it to one more decimal place? Right? So we could draw another little X and Y table. And we're going to put an X here. We'll label this 10 to the X power. And they want us to go 2 decimal places this time. So we pick up where we left off. If we left off at 1.4, this time we're going to do 1.41, 1.42, 1.43, 1.44. Oh, that did not work. Let's get rid of that. Let's see. And we'll put 1.45. I don't know how far we need to go, but let's see where that takes us first. So we would grab our calculator, and we're going to look at that idea. And so 1.41 would be 25.7. 1.42 would be 26.3. 1.43 would be 26.9. 1.44 would be 27.5. 1.45 would be 28.1. If we did 1.46, that would be 28.84. 1.47 would be 29.5. You can see we're getting close to this one. And I'll just put right here, if we did 1.48, we would get 30.2. So we've done passed up 30. So what does that tell us, right? That if we were going 2 places behind the decimal, then 10 to the 1.47 would be less than 30, and 10 to the 1.48 would be just above 30. So they ask us, I think, to do this one more time. And number 5, repeat this process to approximate the value of log to 4 decimal places, right? So we'll make some room. I'm going to put that down there. So if we're going to do that, we would need another table for 3 decimal places. So remember, we're going to be plugging in some x's where we left off last time. And then we're going to do 10 to the x power again. And so where did we leave off? We found out that we were at 1.47 below, so we'll go 1.471, 1.472, 1.473, 1.474, 1.475, and we'll see how far that takes us. And again, I'm calculating these by just putting these into a calculator. And so we're going to start with 1.471, and we're going to go to the third decimal place. So 1.471 is 29.58. Let's see, this will be 29.6. The next one is 29.7. And then we get 29.7 again. It's really 7, 9. So you can see that we're actually increasing. These two are not the same. Then you get 29.85, 1.476. It's going to give us 29.9. You can see we're getting close now. 1.477 is 29.992. And then we can see for 1.478, we're going to get 30.061. So it is between these two, right? I'll draw a box around them. It is between these two that we can see that we are just below 30 and just above 30. Now remember, they did say in exercise 5 to repeat this process until we get 4 places behind the decimal. So we're going to do this one more time. So we'll draw an axis here. We'll switch colors. Got that. And we come straight down. And so if we pick up where we left off at, right, we stopped at 1.477. So that means I'm going to look at 1.4771, and then 1.4772, 1.4773. We're just going to write some of these to give us a head start. And let's see how far that takes us. So again, we grab our calculator. We're going to start at 1.4771. We are now going to the 4th place behind the decimal. And so this is going to give us 29.999. And then the next one's going to give us 30.005. So we got to that one pretty quick. And so we now know to 4 decimal places of what log 30 is going to be by approximating. So they ask us to verify our result with our calculator. So they want us to actually use a calculator, and they want us to type in log 30 and find out what we get in our calculator. And any basic scientific calculator can do this. You don't have to have anything fancy. There's a button on everybody's calculator, as long as it's scientific or higher. It says LOG for log. You'll type 30. You'll press enter. And when we write it down, we get 1.4771. If I kept going across the screen, it would be 2, 1, 2, 5, 5. And it does continue. But we can see the approximation that we did, right? If we rounded to 4 places behind the decimal and got this one, and look right here, 1.4771, as we continue to go across. So if we were to do this a 5th time, we would probably discover that the 5th number would be a 2 by drawing the tables and illustrating this piece as well. So now if we look at exercise number 7, this is where they're going to ask you to just take a calculator and just flat out input these log 1, log 2, log 3, log 4. My recommendation would be to grab a calculator, pause the video, and fill these in. Otherwise, what I'm going to do is I'm just going to continue filling these in so you have a record of them. Log 1 would be 0. and then log 2 would be 0.3010, and then you would have 0.4771. Notice that 0.4771, that's interesting. We just did a log 30, so pay attention to that. Next one is 0.6021, 0.6990, 0.7782, 0.8451, 0.9031, and 0.9542. Now, the goal here is for you to discover a pattern. Notice this is 1 through 9. This happens to be 10 through 90, and this happens to be 100 through 900. And then in a minute, they're going to ask you number 8 is what patterns can you see in the table from exercise 7 as x is being multiplied by 10, and then write the patterns using the logarithmic notation that you notice in each one. So it turns out, right, if once I go to this column, this becomes a 1, and this becomes a 1.3010, this becomes a 1.4771, a 1.6021. Do you notice that relationship to the other table? 1.6990. I'll do one more. 1.7782. Now, if I go to the next table, the 100s, observe the pattern that's going to happen. This is going to be a 2, and then we're going to have a 2.3010, and then a 2.4771, and then a 2.6021, a 2.6990, and so on down the list. So you start to be able to see a pattern such that you can make these basic observations right here. So I'm going to slide this up, give myself a little bit more writing room if possible. And so we're going to notice that if we did that log of 10x, it's going to be equal to 1 plus log x. Also, if we had log 100x, that would be equal to 2 plus the log of the first table. And so we see this idea in that design. Right, these were the basics. We added 1 to get to the things in the tens. We added 2 to get from the original table to over here. So then they ask us number 9, what would you expect the pattern to be to find log of 1000x, make a conjecture, and then write down what you think it is. And so our conjecture is that the decimals would begin with a whole number 3. Right, such that if we were to say this, the log of 1000x would equal 3 plus the log of x. So again, notice this pattern in this design. So it says in 10, use our results from 8 and 9 to make a conjecture about the value of log to whatever power. It would be log 10, log 100, log 1000, log 10,000. For any value of k here, and so that conjecture would be this, and this is one of our properties. The log of 10 raised to whatever power times x is equal to k plus the log of x. So this is a property that you're going to want to note and observe in this design. So in number 11, they're going to give us the same tables, right? We're not going to write as many this time, but because we're on a new screen, I'll write a few of them. So 0.3010, and then 0.4771. We'll go to 5. 0.6021 and 0.6990. They want to know, what if I did log to the 0.1, right? 0.2, 0.3. So instead of going to 10, we're going to go to 1/10 or 1/20th or 1/30th, a decimal version. So this would actually end up being -1. And so this would end up being a -0.6990. This would be a -0.5229. This would be a -0.3979. And this one would be a -0.3010. You start to see kind of an idea maybe developing here. And if I went out to -2, would be this one. And then we would get a -1.6990. Then we would get a -1.5229. Then a -1.3979. Then a -1.3010. So they ask in number 12 is, what patterns do you see occurring from this particular exercise right here? And so what we're doing is the same idea, is that if we had log of x over 10, so a division, right? That's how we would get 0.1, would equal -1 plus log of x. So then also if I had log of x over 100, that would be this table right here. That would end up equaling -2 plus log x. And so we see that general design continuing to flow, even though we're going in a slightly different direction in that perspective. So what patterns would you expect to find for if we said log of x over 1,000, right? Then we would just say that would be -3 plus log of x. And so combine your results from exercise 10 and 12 and make a conjecture about the powers of 10 again. And so we end up with the same rule that we just talked about. If we had log of 10 to the k times x, that is still equal to k plus the log of x in that perspective. So there are two examples. It says, use the logarithm tables and the rules that you have discovered to calculate the log of 40,000 to 4 decimal places, right? So if we utilize this info, we could rewrite the log of 40,000 as the log of 10 to the 4th power times 4, right? We're trying to illustrate that we could use that log property piece. And so now, if we use that rule, we now know that means this is going to be 4 plus log 4. Now I just need to look at what log 4 is so we can go back to our tables. Log 4 was 0.6021. So I replace that with 4 plus 0.6021, and we find out this is 4.6021 as the final answer. Same idea if we had a decimal version. So if we had a log with 0.1, 2, 3, 4, 5 zeros and a 4, this would be equal to, remember we want to move this decimal place over, we would count 1, 2, 3, 4, 5, 6. So this would become log 10 to the -6 power times 4. So that means we would rewrite the rule. We would write -6 and we would put plus log 4. And so that would become -6 plus 0.6021. And when we add that together, we get -5.3979. All right, so that concludes this general lesson. Remember, the lesson we talked about, just to re-emphasize the rule, is that if we have a log raised to a power, then we could take that power and move it to the front and add it to the log of x. So that's going to be the property that's going to be emphasized in lesson 10.